Alrighty, Polygons 101. Okay, and just as a heads up, we're looking to finish this unit before winter break. Okay, and then we're also looking to but to fit in our second benchmark before winter break. So we have 3 assessments coming up: a quiz on this unit, and the test on this unit, and then a few days we'll review, and then we'll do the benchmark for this unit. Okay, so the good news is, right, that benchmark score will replace any unit from any previous unit test grade. Not any, sorry. It will replace your lowest test grade from any of these, most recent units. So if you didn't do so hot on this test in particular, for example, if you do well on that next benchmark before, winter break comes, that grade will replace your grade that you just got on this test here. Okay? So something, you all might want to keep in mind. All right, when we go to that benchmark. Of course, you want to make sure you do well on this next test, so that way you don't have to worry about using your benchmark grade for that test, right? So, anywho, let's talk about polygons. Okay. So, polygon. Okay. Broken up into 2 words. Poly means many. The prefix poly means many. And then the gon part, I believe it means like sides or angles. Okay, so many sides or many angles. I can zoom in something. I don't need to go that far out. There we go. Okay. So, what's a good kind of like mathematical definition? So, a polygon is a simple closed figure, okay, that is formed by at least 3 non-collinear points. And its sides intersect only at endpoints. Excuse me. Okay. Closed figure at least 3 non-collinear points. Sides intersect only at endpoints. Okay. Sides intersect only at the endpoints of the sides. All right, so is it a polygon? Okay, that's the question we want to be able to answer here. Right? Is it a polygon? Right? Is it a polygon? Yeah. Yes. Okay. Is it a polygon? Yes. Is it closed, right? It is, right? It's closed, right? There's no open spaces, and there's no open like breaks in the breaks in the sides or anything like that. Okay. Is it formed by at least 3 non-collinear points? Well, I see 1, 2, 3, 4, 5 non-collinear points there. Okay. And its sides intersect only at endpoints. So here's a side, right? It intersects at the endpoint here, side intersecting at the endpoint here, and so on and so forth. You get the idea. Okay. Is it a polygon? No. Okay. Side, I guess there's one side for a circle, and it's curved, right? We don't talk about curved sides here, so no curves. Okay, circle is not a polygon, interestingly enough. Although we kind of teach it along with those, don't we? Is it a polygon? Yes. Is it a polygon? No. Not closed. Is it a polygon? No. Okay. Sides cross each other. Okay. So sorry, a bow tie, not a polygon. All right, let's name some of the parts, right? So the anatomy of a polygon. Okay, the anatomy of a polygon. All right, I'm going to draw a polygon over here. Just get some more pronounced points here. Okay. On a polygon, we have a vertex, or its plural, vertices. These are points, right, that determine the polygon. We know what a vertex is, right? We've seen them so often. They're like the pointy part of the angle. They're the end point of the sides here. Ugh, my pen is smudging awfully. All right, so here is a vertex. We have a side, right? And a side is a line segment that connects consecutive vertices. So here is a side. Right, duh, Mr. Witt. I know this might be like way too basic for you, but there you go. Okay, and then we have something called a diagonal. A diagonal is a line segment that connects two non-consecutive vertices. Okay, it's a line segment that connects two non-consecutive, not next to each other. Okay, not in order vertices. All right, so let me name some of these things here. So I'll call this like A, B. I'm going to name the vertices A, B, C, D, E, F. Okay. So if we want to draw a diagonal, let's say we want to use A as one of our endpoints of our diagonal. Where can we connect A to create a diagonal? What other points can we connect A to make a diagonal? E, D, and C. Okay, and only those three, right? F, A to F would create a side, not a diagonal, because A and F are consecutive. They're next to each other. A and B also would not create a diagonal. It would be a side, because again, they're next to each other. So there is a diagonal. Okay. All right. The name of this polygon, how do we name a polygon? We name it by its vertices. So it gets a little cumbersome when you have like a decagon and stuff like that, but this polygon is called Polygon A, B, C, D, E, F. Whoops. Okay. That's Polygon A, B, C, D, E, F. You name it by its vertices. So I know it kind of is a little bit much, but there it is. All right. Let's talk about classifying polygons. Different ways you can classify. Okay, there's a multitude of ways, or a couple different ways, I guess, we'll classify polygons. All right, first we'll go back to some familiar ones here, right? For example, whoops, equiangular polygons. Okay, equiangular polygons, and those are polygons where all the angles are congruent, right? All angles are congruent. Here's an equiangular quadrilateral. What's the name that we give to an equiangular quadrilateral? A square is a rectangle. Yeah. So a square is true, an equiangular polygon, but it's actually more special than just equiangular. The more general term is a rectangle for an equiangular. But yes, a square would also be equiangular too. That's true. Okay, next we have equilateral, of course. No surprises there. All the sides are congruent. Okay. All sides are congruent. All right. And I'll do another quadrilateral here. Does anyone know the name of an equilateral quadrilateral? All right, Jenny, what do you say? Parallelogram? Close. Parallelograms, the opposite sides are congruent, but not necessarily all four. A rhombus. That's right. Can you spell it?
R-H-O-M-B.
Yeah, rhombus. In this case. Yeah, very good. Okay, it's like a spelling bee. Spell rhombus. Okay. And then, of course, if something is both equiangular and equilateral, very special case, right? If something has both equal angles, all the angles are equal, and all the sides are equal, right? Very special case. And for that very special case, what do we say? It's regular. I do not understand that name. And what is the name of the quadrilateral that is regular? A regular quadrilateral is also called a what? Square. You got it. He's just a regular kind of guy. Or gal. Okay. Very good. All right, moving on then. All right, we can also talk about concave and convex. Okay, this is a concept that you have heard about before, maybe in science. You have concave and convex lenses. And the idea is similar to that idea, actually. So a concave polygon is a polygon that has at least one diagonal outside of the shape. Okay, this is kind of like a mathematical definition for it. Okay, so what do I mean by that? Well, if I draw this shape right here, which, by the way, how will we name this polygon? What kind of polygon is this? It's a quadrilateral. Yeah. Okay. It's a concave quadrilateral. There actually is a name for this. It's called a chevron. All right. And if you ever that's like, hey, Mr. Wood, that's a gas station. It's like, yes, it is. And if you look at the chevron symbol, it's a chevron. It's like a quadrilateral like that. Okay. Or it uses that shape, or kind of like that shape, I think. It's not exactly right, but anyway. This is called a chevron. So we have some diagonals we can draw. So for example, here's a diagonal. That's an interior diagonal that we can draw, right? Connecting those 2 points. But connecting these 2 vertices, the diagonal is outside. So there's that exterior diagonal. Okay. Likewise, we can talk about this shape that I used earlier when we were playing Is It a Polygon? Okay, right here. And again, you can see here's the exterior diagonal that connects the two vertices. Not all the diagonals are exterior, but if any of them are outside the shape, if any diagonal that you draw is outside of the shape, that shape must be concave. Okay? So, if you guys remember talking about lenses, again, have you guys talked about lenses before in like science and stuff like that? Okay. So a concave lens, right, looks like this. Right, it's kind of like bent in on itself. So that's like, maybe another way to think about it, a not so official way, but a way to think about it too, right? These shapes are all bent inwards, or caved in kind of thing. Concave, caved in, right? Bent in. So you can think about it like that. There's that word cave, right? Concave, bent in, or concave, caved in kind of thing. Okay? Whereas convex, those are more traditionally what we think of when we think of a polygon. Okay? A convex polygon, here's the crazy definition, it's not concave. Okay. So again, I'll just draw like a... Okay, right, you can see all the diagonals that we draw here. Okay, all the diagonals that we draw, none of them are outside the shape. All right, one more thing, and then I'll have you guys do a little activity here. We're going to make sure we have all of our names down. Okay, so we'll give you the names of the polygons by the number of their sides. Okay? So, the name for a two-sided polygon. What's that called? Doesn't exist. Yeah, that's right. Mr. Wid, why would you have us write that? That's so dumb. Sorry, guys. How about a three-sided polygon? What do we call that? A triangle. Okay. And a four-sided? Quadrilateral. Right, we talked about that. Okay, I'm just going to start writing the numbers now. 5 sides. Pentagon. Penta, prefix meaning 5. Like a pentathlete, they compete in 5 events. Okay, 6-sided polygon. Hexagon. All right, how about a 7-sided polygon? Septagon or heptagon? I'm going to put heptagon because I think that's the more traditional, the more typical way of saying it. But septagon, I would accept. Okay, septagon, I would accept. Okay, 8-sided shape. Octagon. Thank you, octopus, for helping us out with that. Right? Octopus, 8 arms. Octagon, 8 sides. Or if you like to watch MMA, they fight in an octagon. Okay. 9-sided nonagon. Nonagon. 10 sides. Decagon. Yep, like a decade, right? 10 years. Decagon, 10 sides. All right, 11-sided. Well, I looked this up. It's sometimes called an undecagon, or I also saw a hendecagon. Okay. You don't need to know that, though. It's okay. And then the 12-sided dodecagon. That's more fun, I think, to say. Dodecagon. But really, you only need to know up to 10. After 10, we really then just go to n, and we just call it n-gon. So in other words, if you had like a 99-sided shape, you would call it a 99-gon. Okay, because it just gets kind of cumbersome to have to come up with all these names and things. Okay, so it's a 99-gon. N-gon, a 9-gon. Okay, sometimes you'll even hear these shapes referred to as like a 5-gon or a 6-gon or a 3-gon, but you also should know their names too. Okay, questions on any of that? All right, so don't put this too far away. We're going to come back to this in just a moment, but I have a little activity for us here. All right, for you all to try to discover another property of polygons. So what I've got here for you is a table with some polygons drawn. I want you to give me their names. So, this shape is a this kind of polygon. Okay, this shape is a this kind of polygon. Give me their name by their number of sides. Give me the number of sides. Tell me the number of triangles that you can draw from one vertex. So what do I mean by that? Well, let me give you an example here. This shape right here, right, the quadrilateral, from one vertex, I can draw a diagonal here. Okay, there's no other diagonals I can draw. How many triangles do we create there? 2. Okay, in this shape, right, okay, I'm going to pick one of the vertices. I'll just pick this one. I can draw a diagonal to here, and I can draw a diagonal to here. I cannot draw any more diagonals from that same vertex, from one vertex. How many triangles did I create there? 3. Okay, you get the rest of the idea. Then you can tell me how many degrees are in a triangle. Okay, we all know the answer to that, so this column will be the same number. And then, what is the interior angle sum of the shape? So, for example, here for the square, how many triangles are there? 2. So both triangles have to add up to 180 degrees. But if there's 2 of them, the total here would be what? 360. So we would expect the interior angle sum of a quadrilateral to be 360 degrees. And then you can go on for the rest of those and finish off that. Okay? And then at the end, you're asked to discover or come up with a pattern between the sum of the measures of the interior angles of any convex polygon. So use this table to help you see if you can come up with a formula or a pattern or a relationship, okay, that relates the number of sides with the interior angle sum. Okie dokie? Capiche? So here we go. One for you. And I'd like you to just take your seats for this one. Try it on your own. You're welcome. Pass it down, please. Maybe you already know the formula, you already know the relationship, but just give this a try and see if you can see.
Is this the corner right here?
I'm not sure if it's a corner or it's supposed to be a straight line.
What's that? Good question. This should be a 7-sided shape, so whatever would make it 7, yes. Okay. The polygons add a side each time, so when you're doing it,
Should this be a square or a quadrilateral?
call it a quadrilateral, just the generic name for it. And again, the reason it does look like a square, but we're going to be more careful in this class. We want to make sure that things are marked. Those are all right angles, and like those would all be congruent and stuff. So that's why we want to be careful by calling it a square just yet. Just like when you see a triangle, and if it looks equilateral, you don't necessarily assume it's equilateral. It's marked that way, kind of thing. Whoops. I guess I'll put this up. And this was made by Miss Williams Kennedy, who's a very good geometry teacher at Frederick High School. That's why you see that name at the bottom there. Yeah, just what you said. Yeah, so there's let's take a look here at excuse me, this paper. So hopefully you got something that looks like that. Did it all? Yeah, something like that. Okay. So, does anyone see any patterns here with what's happening? I want to describe what's happening in the sum of the measures of the interior angles. Yeah, Madison?
As the sides of the polygons increase by 1, the interior angle sum increases by 180.
Aha. Okay, so every time we add a side, we're adding 180 degrees to the interior angle sum. Okay? So add a side. Add 180 degrees to interior angle sum. Okay? So, if I wanted to come up with the sum for any particular polygon, what could we maybe do here? So, let's go to Avery. Try her.
I came up with like an expression. It was 180 times x minus 2, where x is the number of sides, times quantity x minus 2.
Okay, yeah, so there it is. So we take the number of sides, okay, and we're going to subtract 2. Let's take a look at where that's coming from here. Look at your table, right? Here are your number of sides, right there, 4, 5, 6, 7, 8. How many triangles are there? So 6 here, 5 here, 4 here, 3 here, 2 here. How do the number of triangles relate to the number of sides? There's 2 fewer of them, right? 4 sides, 2 triangles. 5 sides, 3 triangles. 6, 4, 7, 5, 8, 6. Okay. Each one of those triangles, what's their interior angle sum? Any triangle, what's the interior angle sum for a single triangle? 180. So if there's 2 of them, 2 times 180 gives you 360. 3 times 180 gives you 540. 4 times 180 gives you 720. 6 times 180 gives you 1,080 degrees. So if you take the number of sides and subtract 2, that gives you the number of triangles, and then you multiply it by 180 degrees, which is the number of degrees in a triangle, that will tell you what the interior angle sum of any polygon will be. Okay? And so it's exactly what Avery said there. Okay? N minus 2 times 180 degrees. Okay? How neat is that? That's pretty neat. So, I'm going to finish up the notes then, and then we will get back to, where did I put that? No. Nope. Huh. Let's see if I can figure out where I put that paper. Oh, there it is. Okay, so finishing up here then, the interior angle sum for any convex polygon, right? Concave, all bets are off. N minus 2 times 180. N is the number of sides. Okay, so let's do 2 examples here real quick. What is the interior angle sum of a decagon? What is the interior angle sum of a decagon? Well, how many sides does a decagon have? 10 minus 2 times 180 10 minus 2 is 8. 8 times 180. I actually have this written down here for myself, so I'm not doing this mentally. 1,440 degrees. So all the angles in a decagon add up to 1,440 degrees. Let's ask a follow-up. What is the measure of a single angle in a decagon? Can we answer this question? We know what they all add up to, but can we answer what the measure of a single angle is in a decagon? Can we answer this question? Avery?
Not unless it's specified to be equiangular.
Right. We don't have enough information here yet, right? We don't know. A decagon by itself is not guaranteed to be, first of all, convex or whatever. I guess we can assume. Well, anyway. It's not guaranteed to be regular, right? But now let me throw this in here. In a regular decagon, now can we figure out what the individual angle measure for a regular decagon is? Yes. What should we do? How can we figure it out? We know that all the angles in a decagon have to add up to 1,440 degrees, and we know that they're all going to be the same. Press.
Take the answer and divide by 10.
Yeah, take the answer, the sum of the angles, divide by how many angles there are in the triangle, and so you get 144 degrees. 144 degrees. Okay. Last thing here, we have the exterior angle sum. Okay, we've talked about exterior angles before, way back in like the first unit. Okay, where we had the exterior angle theorem for triangles. Triangle exterior angle theorem. The exterior angle sum of a polygon. Notice I'm not specifying what polygon it is. Number of sides, nothing. Just any kind of convex polygon is 360 degrees. For a triangle, all 3 exterior angles will add to 360 degrees. For a decagon, all 10 exterior angles will add up to 360 degrees. Okay? Remember that for a polygon, let me just draw a little pentagon here, I guess. Okay, like that. Okay. Okay, the exterior angles are always an extending aside and then the adjacent side right here. So that is an exterior angle. These are all exterior angles. Okay, like that. All right. And the exterior angle here is supplementary to the interior angle, right? So here's an interior angle. It'll be supplementary to its exterior angle, and vice versa. So last question here for you guys, and I'll get you started on your homework. What is the measure of one exterior angle of a regular pentagon? What is the measure of one exterior angle, excuse me, of a regular pentagon? So these 2 different ways to do this here. Okay. So what is the measure of one exterior angle of a regular pentagon? Jackson?
72.
72. How'd you get that?
Well, since the exterior angles add up to 360, there's 5 of them. Just divided 360 by 5.
Beautiful, exactly right. We got a pentagon right here, so you can kind of see the example. But I just got done telling you the exterior angle sum of a polygon is always 360, no matter the number of sides. Since all these exterior angles have to add up to 360, there's 5 of them, and we're trying to find the measure of one. They're all equal. 360 divided by 5 is 72 degrees. Alternatively, you can find the measure of one interior angle. So we can do 5 minus 2 times 180. So it's 3 times 180, which is 540. You can divide 540 by 5 to get the measure of a single interior angle, which is 108. So there's the interior angle measure. And what do we know about interior angles and exterior angles? They will be what? Supplementary. And look at that. 108 is the interior angle measure. And sure enough, 108 take away 180, or 180 minus 108 gives you that 72 exterior angle measure. So another way to do it there too. Okay, so another way to do it right there. Okay, so a couple options for that one. All right, questions on any of that? No? Okay, so your homework, I will post to Google Classroom here in 2 seconds. All right, because I don't think I did that yet. So let me do that real quick. All right.